Hello, my name is Macie Zack, and today with Borowsky and Oren Lerner, we will be walking through an investigation around resistive forces. The overall purpose of this experimental design was investigating the relationship between the mass of a falling object and the resulting resistive forces upon it, using the tools available, including tracker, and the knowledge we learned in class, which includes kinematics, resistive forces, and experimental design models, to create and use relationships between mass, velocity, and resistive forces. With the assistance of tracker software and force equations, the descent of 4 sets of paper plates of increasing masses dropped at the same heights were analyzed. The only changing variable was the mass of the object, which has a direct impact on the acceleration of the object, and therefore the velocity. And the velocity of the object is a component of resistive forces. With the velocities of the descending paper plates of increasing mass identified with tracker and the calculated respective forces, a number of trends were identified between the object's acceleration and the influence of resistive forces as the mass increased. Using the known concept that gravitational force remains constant across an object's movement, we can assess the impact of how the increased mass will affect the force of gravity acting upon the object and possibly the comparative force of air resistance. Additionally, we know that gravitational forces remain constant within trials but increase as masses increase amongst trials. Furthermore, it is proposed that as gravitational force increases, resistive forces would also increase. Finally, it is important to note that terminal velocity has an equal and opposite gravitational and resistive force. In essence, when velocity is constant, acceleration is zero. In our closed system, there are the plates, air, and the ground. There is a gravitational force on the plates by the ground, and there is a contact force on the plates by the air, and this contact force is in the form of drag and viscous forces. Overall, the gravitational force pushes the plates down towards the ground, while the contact force acts as the resistive force against the direction of the motion, pushing the plates away from the ground. The basic parameters of our experiment include vital information in order to calculate the gravitational, drag, and viscous forces.
Using the equations for the force due to gravity, the drag force, and the viscous force, we were able to calculate the values for each of these forces for the different trials, being 2 plates, 4 plates, 6 plates, and 8 plates. We made the following assumptions throughout our model. The tested environment had no draft, therefore no horizontal influence on movement. The viscous force were practically ignored in our analysis due to the minimal values. We assumed that all plates started at the same height, 1.9 meters, and we assumed that all plates fit the shape of a 2D disc parallel to the motion of the plates. For trials 1 through 4, we chose to analyze the data using the following 2 graphs. In the graph on the right, we compare the drag force to the net force. Here we can see that the only factor affecting the net force is the drag force. In the graph on the left, we monitor the velocity and the acceleration as a function of a change in position. We can see that at first the velocity is quite negative, but then begins to level out. Meanwhile, the acceleration is quickly approaching zero as the objects reach its terminal velocity.
The initial flaws identified by planning and conducting the experiment were the initial flatness of the plate upon dropping, the variability of tracker software frame values, and the imperfect plate ridges adding additional surface area inaccuracies. Despite the identified design flaws, trends amongst mass and motion were found. It was difficult to confidently conclude a relationship between the object's acceleration and mass due to some of the flaws aforementioned. However, a more clear trend is seen in the relationship between mass and velocity. It was found that as mass increases, the magnitude of velocity also increased. Relative to terminal velocity, this information lays the groundwork for the investigation of the impact of mass on forces related to the object's terminal velocity. Based on the components of gravitational force, the greater the mass, the greater the experienced gravitational force. It was found that as mass increased, so did velocity, and ultimately the object's drag force, being that velocity is a component of drag forces. These trends highlight a relationship between an object's mass and the resistive forces. In connecting these concepts to terminal velocity, the object will reach terminal velocity as drag reaches the value of gravitational force. If an object's mass increases, both gravitational and drag force will increase. However, none of the trials conducted reached terminal velocity. This implies that the objects need more distance in freefall to reach the terminal velocity in this fluid. Through trends identified, the increase in mass caused increases in both gravitational and drag forces. The reason an object of greater mass might not reach terminal velocity faster than their lighter counterparts, despite having greater gravitational force, is due to the simultaneous greater impact of resistive forces. For future experiments and investigations, we wish to pursue studies with better tracking and experimental environment for more accurate measurements of motion. The object used could represent a true 2D disk to reduce unexamined surface area. Finally, in hopes of investigating terminal velocity further, we would hope to experiment with greater distance to allow the objects to reach terminal velocity.